So, hello everyone, good morning. So today's speaker is Patrick Pérez. He's Valeo VP of Artificial Intelligence and Scientific Director of Valeo.ai, which is the AI research lab focused on Valeo automotive applications, mainly on self-driving cars. Before joining Valeo, he was a researcher at Technicolor, Inria, and Microsoft Research Cambridge. So his research interests are multimodal scene understanding and computational imaging. Thanks, Patrick, for accepting my invitation. Today's talk is Annotation-Efficient Perception for Driving. Patrick, the floor is yours. You can start.
Well, thank you very much for the introduction and for the invitation. We've been discussing about setting up this seminar for quite a long time, so now it's real, although being remotely held. Today, I'd like to talk about one very important aspect when it comes to learning machine learning models for applications like autonomous driving. And this problem is the one of annotation of the training data and how to go about it and how to do without annotation sometimes. In order to set the stage, well, hopefully, by the way, hopefully you see my presentation in slideshow mode.
Yes.
Okay, that's good. So just to set the stage, I'd like to remind, although it's fairly obvious, why so many people and companies and labs are putting so much energy into developing what is called advanced driving assistance systems, ADAS, and autonomous driving, AD. The first reason, obviously, is safety, in order to reduce the casualties and injuries due to road accidents. There are really still a lot of casualties already around the world on a daily basis, so this has to be really improved. So this is the big and the main goal, but there is also the fact that all these technologies should, at the end of the day, make transport of people and goods way more efficient and also more easier at large, including for people who have no real access at the moment of easy mobility. And this, coupled with electrification and connectivity of vehicles, should allow as well something which is more sustainable in terms of energy and also pollution. So this is great. But it seems that it takes longer than expected, at least for autonomous driving, and we might wonder why, despite all the bold statements, we are still not seeing on a daily basis such vehicles on our roads. In a nutshell, the reasons are here. They are just in a few words. So here we are talking about very complex systems with the machine learning models inside. And we know that AI, we all know that it is progressing very fast. The caveat is that we are talking about safety critical systems, which are embedded, limited hardware and resources, and this has to be done in real time. These systems obviously are deployed in the wild, in the open world, interacting with other road users, and these technologies, these objects, they are in the wild for long time periods. They are not like mobile phones. They are on the roads for 10 to 20 years. So all these constraints put together makes the promises of autonomous driving very hard to deliver. So this is good for research, not always so good for business. And we are going to discuss some of the aspects. So when I say open world and in the wild, this is what it might mean. Cluttered scene in busy city centers across the world, like here it's London, Toronto, I believe, Tokyo and Paris, on my way to my office on a normal day. So it's quite complex, very unpredictable. And here all the weather is clear in the four scenes. It could be way worse with rain and fog, etc. So we have to face this reality. Crazy people on new devices, like on the bottom right, etc. So it's a wide world out there, right, on the roads. So this is essentially the challenge of what is called level 3 to 5 autonomy. So for those who are not completely familiar with this taxonomy, autonomy level 3 and up is when the car is really becoming in charge as opposed to the driver, even in terms of liability. 3 is sort of partial automatization, but you can already have your hands off the steering wheel and your mind off. And 5 is essentially full autonomy everywhere at any time. You can even think of vehicles without any steering wheels or pedals. So it's very difficult to get there. And you see the small illustration here is one of our experimental platform, which is more or less level 4, driving in Paris, but it's fully experimental. The only thing which is not experimental, it's the fact that it's using actual series sensors that we make, like cameras and lidar. So anyway, if we want to reach these levels of autonomous driving or highly automated driving, we need to essentially to be able to address all the potential operational domains. So it encompasses all types of driving situations, from busy city streets, as we just saw, all the way to highway or countryside. So a lot of diversity. It has to be deployable everywhere on different continents, different type of countries, and also in all types of weather and illumination conditions. So it's quite demanding. And what are the things that we might leverage to get there? Because it's about a lot about machine learning, but not only, but focusing on machine learning part. So we should try and get better training data, which will be the main focus of my talk today. With better training data comes better models, but also using different ways to supervise the training. When I say better training data, better models, better means different things. For instance, better models means better, higher accuracy, higher performance, but also might mean more robustness, which is very important. At the end of the day, if you want to put these things on the roads, you need to have a very thorough testing, including on open roads, which is quite a challenge. And when we look at what is actually embedded in the car, ideally, we would like all these machine learning models to be equipped with the ability to sort of self-assess themselves in terms of uncertainty, so predicting failures, etc. It seems quite important, at least that's our take at Valeo, and as for many other players in the field, to use multiple sensors in order to get both redundancy and also complementarity when it comes to different driving conditions. So again, typically camera, lidars, radars, etc. And also, it's very important not to rely only on data-driven things, but also some knowledge of the world, which encompasses both the knowledge of the rules, the driving rules, of course. So you have to respect the driving rules, that's for sure, but also the knowledge of the physics of the world, the dynamics and the kinematics, etc., which are part typically of the planning, which is involved in the driving. So these are all the levers that we might use to get closer and closer to our ground goal. All right, let's now move forward and discuss about training data, in particular real training data. So as we know, although things are now changing progressively, the strongest or the most powerful deep learning models, they are essentially fully supervised in their training, which means that you need data and annotation and full annotation to train them. So let's see what it means in our context. First of all, raw data. So collecting the raw data, it's easy in a way, but not always easy in a sense, because for the type of applications we are talking about, you need to really collect a lot. But it's not only about quality, it's quantity. Sorry, it's also about the diversity, as I said before, and the coverage. So in order to cover all or as much as possible all the diversity of the of operation domains, you need a lot of data which is carefully selected. And also, in terms of just the technicality of the collection, you need to build this type of vehicles where you have all the sensors, both the sensors that you will have at runtime, but also more expensive so-called reference sensors, like a big lidar in this case that you can see on the top of the car. And you need, of course, all to align all these sensors, meaning that they have to be synchronized, but also they have to be aligned in terms of geometry, etc. So, I mean, it's not an easy task to build this type of recording setups, and then you have to run them all over the world. So there is a scale issue as well. But still, I mean, then if you have that put in place, then it's just about going on road and recording and storing these things. So it's fairly okay. But things get worse now when you consider the labeling. So for many of the tasks, in particular the perception tasks, which is the one I'm going to focus on today, you need to annotate, in particular using annotators, human annotators. And this work is extremely difficult for reasons I'm going to illustrate now. So it takes time, it takes a lot of money to do that, and it's part of the problem is there. So let's try to understand why it's so difficult. Let's start with cases where the input is fairly easy to comprehend for human beings, typically static images, like a single frame from a video. And if you consider some of the tasks that we have to solve, you can see already that annotation is difficult. So first example is the typical semantic segmentation. To do this type of annotation, it's a few minutes per image or more than that, and it's a few dollars per image. So it's both time consuming and expensive, as you can imagine. And typically you would need that for hundreds of thousands of images or millions of images, which is something which is a bit crazy at scale. Another task, which is typically when you want to analyze in 3D the body of pedestrians, say, the position of the joints, even the volumic position, to do that by hand is very difficult. I mean, first of all, you need specific tools to do that, and it's very difficult. Another example, which is actually close to the collaboration we had with Alexandre last year, which is the detailed analysis of pedestrians in order to where you want to predict a lot of attributes about each single person on the street. The annotation is very difficult because of the level of detail, but also because for some of the pedestrians, depending also on the distance, it might be very difficult to get it right for a human annotator. And here we are just talking about sort of classic semantic, or to some extent semantic annotation in a single frame. And it can get worse also because of the illumination. So these are examples at night, which is an important problem. So Dark Zurich, it's a data set where you have semantic segmentation at night. So for human annotator, it's even more difficult. Same with 2D and 3D boxes for vehicles and pedestrians in the second column on two different data sets, public data sets. And the third example is from one of our public data sets where we have fisheye cameras, and one of the tasks is to annotate the dirt and the soiling on the lens, which is important. And when you want to do that at night, it's sometimes difficult to distinguish between soiling and actual darkness. So these are other examples in images. But let's continue with other modalities. These are two examples, one from Valeo and one from Waymo. On the left, you see one example with radar. So what you see on the right are different views of the radar signal. And if you are not an expert, that's for sure, it's very difficult to annotate, but even for experts, because the signature of each object can be very spread in the signal. So very difficult to annotate if you just look at this data. Likewise, with point cloud that you see on the right. So these are the typical point clouds that you get with lidar around the car. And if you want to annotate all these cuboids, like for the vehicles and the pedestrians, etc., it's very demanding, and sometimes it's just very difficult to understand, just to make sense of the point cloud. And on top of that, you might want to do that, still looking at the right example from Waymo, you want to do that through time. So you want to track the object, so it adds one more difficulty for the annotator. Of course, you have tools for that. This is an example here. Hopefully you should see a video. It's a typical interactive tool that we have at Valeo for annotating point clouds. So you have easy way just to roughly select an object, and then the rest is done automatically. But what you just see in examples are the simple cases where you more or less see where is, especially when you are used to it, you see where is the object, a car, for instance, or pedestrians. But if you look at the top right, where it's a bit further away from the car, it's probably way more difficult for the human to make sense of all these points. And in this case, it's a very dense point cloud. If it's more sparse or sparser, well, it's even more difficult to annotate. So at this stage, I hope I convince you that the life of the annotator in the automotive industry is not easy. Right. And even if we had infinite time and budget for that, probably it wouldn't be sufficient because of the mere diversity of the situations. So for the systems that we aim at, it's arguably not sufficient anyway. And there is another reason for which annotated or recorded data is not sufficient, is that for most of the rest of my talk is about perception tasks, but for some of the tasks that you need to address for a full driving system, when it comes to the prediction, the planning, and the actual action, it's a closed loop system, right? And if you want to train that and test them as well, then you need to be in an interactive environment. So usually it's done with synthetic data. So with real data, it's not very easy to do. Right. So data sets. So it's key. Annotated data set still is obviously very important. And luckily enough, there is a lot of publicly available data sets, driving data sets. Here I'm just listing the data sets which are sort of generalists. They are not focusing especially on pedestrians, for instance, but they are really driving situations. And you see that there is a long list, and things have even accelerated in the past 2 years with many things which are really interesting. But if you are, for instance, really after nighttime driving, which is again clearly an important challenge, then you might notice that there are not so many of them, and even the one that I have listed here, they're not. Some of them are specialized on night driving, like Dark Zurich, but the other, it's more like they have one fraction of nighttime data, so it's helpful, but it's still limited. So the point I'm making here is that there is a lot of resources out there, and it's expanding, so that's great, but we are still way far away from the scale we need for real applications. So let's see what we can do with this data or this lack of data. So let's assume that we have this large amount of data, of raw data, at least of driving raw data, and that's because of all the constraints I mentioned, the annotation is fairly limited. So there are different things you can do to use this data. First of all, you try and make the best of whatever you have, and you can do that with, of course, fully supervised learning on the annotated part of your data. But for the rest, you can do self-supervised representation learning that you can then use as such, or you can fine-tune for your downstream tasks. You can do semi-supervised learning, which is a mix of annotated and annotated data. One form of it, which I'm going to illustrate, is domain adaptation, Or you can also do zero-shot learning, few-shot learning, etc. So which are the classic things in machine learning when you have limited supervision. So this is just using what you have for now. And then you can try and expand your annotations from the one you have already, in particular using some automatic way to annotate. It comes under different names like pseudo labeling, auto annotation, etc. So I will show examples. At large, what you can try and do is to, wherever you have knowledge or annotation already available, you can try and transfer to where you don't have that if there is a clear path. So it can be knowledge transfer from other domains using already trained models, or from other tasks, or using multitask learning, etc. Or when you have different sensors which are aligned, you can propagate annotation from one modality, which is easy to annotate, to another. And I will show examples of that. And last,
I have one question.
Yes? Yeah.
What do you mean by here modality and domain? Like, is it?
Can you repeat? The audio is not great.
Sorry, like the difference between modality and domain here.
Oh,
like,
sorry. Modality, what I call modality, it's different sensors. So you have a camera and a lidar. Domain is cities, different conditions, but with the same type of sensor.
Okay, thanks.
Okay. And last one, you can aim at generating new data, including the raw part of the data. And this comes in different guises. One is to take real annotated data and change the, say, the domain. You go from day to night. In a sense, it's a form of style transfer. Or you can try and manipulate part of the content of the scene, add or remove objects, etc., while retaining or modifying accordingly the annotation. So you change the structure. Or you might use computer graphics rendering pipelines or GANs in order to generate new scenes for which you, by construction, control completely the annotation. And all these things can be mixed in order to get the best of all worlds towards the training of your best models. So let's take one problem, for instance, which is transferring knowledge across domains. Actually, in the form which is the following. So it takes different forms, but this example, for instance, where you train on synthetic data, and obviously you want to have good performance on real data. So when we call the terminology here is that you have a source domain for which you do have annotation, and a target domain for which you have raw data but no annotation or little annotation. And if you train in this example a semantic segmentation model on synthetic data, like on Cynthia or GTA5 dataset, or then if you run on a new image, the performance is fine. And if you run on a real image, the performance, the result is not good at all. And this is something you want to improve. So this is one example, but it could be source and domain, target domain could be different countries, different time of day, different conditions, weather conditions, etc. Again, so the field of unsupervised domain adaptation goes this way. You have fully annotated source domain images or data. It can be the same, by the way, on point clouds. And at training time, you do also have target domain images, or data without annotation. And you want to use at best this information at training time. So one way to do it is to do what is called adversarial domain adaptation. And here I'm using I'm taking the example of a work that we did 2 years ago at CVPR, but which is fairly representative of the UDA method. So the idea is that you want to train your main model using full supervision at least for the source domain examples in green here in this example, and at the same time you want to use your unannotated target domain images or data. And in order to do that, you are going also at training time to try and align some features or somewhere in the model across the two domains. So these features can be actually at the very beginning of the model. Actually, it could be even the inputs in the image domain, all the way to the output, or somewhere in between. So let's, in our case, in our work, we were very close to the output, like typically the logits for semantic segmentation, and you want to align, meaning that, and you do that using adversarial training. So you have now also your unannotated target domain data examples, and you can pass both target and source examples through the model, and the features levels. At the feature level, you can train a discriminator, which job is to determine whether, well, the example comes from source or target. So you do you combine the two at training time, and once you have done that at runtime, obviously you run only on target domain inputs. So in our case, what we aligned actually is the predictive entropy at the logit level, and we had another mechanism, which is to also favor low predictive entropy on the target examples, because it's a clear sign of the model not being good and being very confused. So we add a third loss, which is not presented here. And another ingredient which is that we used in our work and which is very useful in UDEA, it's one form of auto labeling, which comes actually from semi-supervised learning, where you train on the annotated part of your data, and the current model is used to automatically annotate the other part, and then you retrain. So we do that exactly here. With the difference that the annotated part and the unannotated part, they are not in the same domain, but you can. So it's a bit more tricky, but it turns out to be feasible and very beneficial. Just one snapshot of results here on semantic segmentation. In this case, the source domain is synthetic images, and the target domain is cityscapes, I believe. And you see the clear difference between not using adaptation and using adaptation, adversarial adaptation that we proposed. And it's a very active field of research, and the performance has since our paper in 19, the performance has dramatically improved. But the mechanisms that we proposed are still relevant, and they can be complementary to other things which have been done since then. Another example for detection here, I'm not going to comment the numbers, maybe for the sake of time. In this case, we showed the adaptation to foggy weather condition. Actually, it's synthetic fog in this case, in the what is called cityscapes foggy. And you see here what happens if you just use it's a simple object detector that has been trained here only on clear time images, and you see that it does the decent job on the right and doesn't detect anything on the left. And after adaptation, this is what you get. So it's way better, at least in terms of recall. So it can make quite a big difference if you think in terms of real world systems here. And
Patrick, sorry, I have a question.
Yep.
For the self-training part, did you study the case that if you have OOD out of distribution example, for example, object from unknown categories that you didn't observe during training? I mean, how you basically can trust these pseudo labels that you create during the self-training? Did you use some sort of threshold, or?
That's a very good, that's a very important point, actually. Even without, I mean, the case you mentioned is it's one of the critical case where you have really out of, as you said, out of distribution. But even without that, you are still facing the issue of selecting the pseudo labels. And so the first version is using a threshold on the scores.
Right.
And then we used a more sophisticated mechanism based on another work where which was at New Reefs on the same year, where we trained an auxiliary model, which is predicting whether a classification or a pixel label is going to be correct or not. So
right.
this filtering model is trained for that. And then you use it at runtime in order to give a score which is more informed of the performance of the model. And this is the ultimate version we used.
Right. Thank you.
I'll get back to your question I will get in a second. I will get back to another aspect of your question, which is about new classes.
Perfect.
Actually, maybe I'm going to go through just to say that we have an extension where we can have, which was at ICCV in 2021, where we extended to multiple target domains, which is the real life. Actually, there is no such thing as a single target domain, and we showed that essentially our framework can be used to train first target-specific adapted models, and then use them. So if you have 3 target domains, then you have 3 target-specific models, and then you can use them in conjunction as teachers for a distillation mechanism, and you distill everything, all the knowledge, to a single model, which is then able to do almost as well on all the target domains with the same capacity. And just to see an example here where we compare. So in this case, the source domain is again synthetic data, and we have 2 target domains, which are very different because different geography, different localization. Cityscapes, which is in Germany mostly, and IDD, which is Indian data set. And we see that we can adapt from synthetic data a model which that you see on the right, which is doing pretty well on both cityscapes and IDD, without actually at runtime knowing which domain it is, because it's target domain agnostic. Okay, let me move forward. I'm going to skip this one because time is running, but it's about using multiple modalities. But I like to go to get there about the question that I just had, which is about new classes. So a work that we did is to first look at how to segment classes for which you don't have example at all. So it's a zero-shot learning problem, but in the context of semantic segmentation. So I'm not giving the details here. You can have a look at the paper, but essentially we use a fairly classic approach where you map your semantic classes to a latent space through word embedding, and from there you can generate features both for the classes for which you have examples, and then for classes for which you never saw any examples. And then you can train a segmenter on that. And these are 3 examples where you see that the model then is able to segment the motorbike without any motorbike example. Then the same here, going from a wrong horse labeling of the cow into a correct one to some extent. And the last example, so the first segmentation is using understand which is not such a bad idea, but it's using the truck label because it's the one which is available from this supervised learning, and then we can recover the actual train label in this case. And then, which gets me back to the question, we extended that to the case where we have new objects because of the different domain. So in this case, what you see here is if you look at the rightmost column, are results of semantic segmentation, where the model has been trained with annotated cityscapes, unannotated IDD, Indian data set, for which you have new classes, in particular the tuk-tuk, the rickshaw vehicle here. And you see, so in this case, at training time, you do have example of these new vehicles because you have unannotated engine images. but they have never been annotated. So you don't have a single annotated example of the tuk-tuk, and yet with the combination of our different tools, to some extent you can segment them nonetheless in new test IDD images. Right.
Thank you.
Yeah.
Patrick, I have a question regarding that part.
Yes.
It reminded me of the past life of computer vision, where when we were doing objectness, we were not trying to classify its semantic. We were just segmenting object, right?
Yeah.
Have you compared to this line of thinking, or is it very different?
I mean, in a sense, I mean, here is different, but we look at that as well as other teams, because for good reason, which is semantic annotation is limited as well in the taxonomy, and there are always things. So there is a long tail issue with very rare objects, or where maybe it's not even meaningful to try and a priori sort of list all the ever possible objects you will find in streets all over the world. So the idea of being able to discover objects in data sets, because they are recurring. So we do work on unsupervised object detections, for instance, which is fully unsupervised, or likewise using, which is something that you have in some of the state-of-the-art, or at some point at least, deep learning object detection models, where you have indeed you have proposals, like you have object proposals, which are agnostic to the class, and this is very useful indeed. Maybe a bit, well, I was about to say not so much for segmentation, but it's not even true. It's also useful for segmentation. So very good point. It's also very useful to consider object agnostic detectors, which are trained, which are usually trained on objects which are with actual categories, but you ignore the category when you train the detector. So this is one way, and the other way is really discovery, where you want to find recurring patterns for which you don't have annotation, but because they're recurring, they seem useful. They're not useful, but interesting to look at.
But in your segmentation, I mean, your zero-shot formulation, have you trained a network where it does segmentation without, I mean, requiring the classification?
So it's what we do is that we generate fake deep features for the new classes by exploiting the semantic proximity with existing classes. So that's the way it works. So we don't use explicitly in this work the fact that there would be an additional mechanism for pointing out segments. We do that in more recent works. Probably I won't have time to show that, but where we do fully unsupervised segmentation. I was about to say semantic segmentation, but because it's fully unsupervised, it's not semantically explicited. I mean, you have segments, but then you can match that with actual semantic segments. And so yes, we do these kind of things. It's quite difficult to evaluate, because then you need to nonetheless to evaluate against true, semantically annotated images, and then you need to do some Hungarian matching kind of thing. But we do that as well, but it was not the case in the thing that I just presented.
Because I mean, one also baseline would be to run like a region proposal or objectness, and then just segment within that bounding box.
So ideally, I think where you have a good point here is that ideally, because in a sense there are three types of classes. There are the one for which you have annotation at train time. There are the ones like I just showed with the zero-shot thing, where you know the labels, so they are part of your catalog, but you don't have examples, or at least annotated examples. And there is this third kind, which is the classes that you're not even aware of at training time.
Certainly, yeah.
And ideally assist I mean, at the end of the day, you want to be able to handle everything. Yeah.
Yeah. Thanks.
Okay. Yeah. Moving on. So second part, which is about using actually automatic annotation in the form of auto labeling. So in particular, whether you transfer or you propagate your existing annotation from one sensory modality to another, they need to be aligned in this case, or you use a model which is already available off the shelf and which is good, and you use that as an annotator, or at least it provides you pre-annotation to be cleaned by a real human annotator, and this automatic annotator can be doesn't need to have the constraints of the model that you will use at runtime. So that's interesting. And another aspect is to do auto annotation, but with pseudo classes, which is actually connects with the discussion we just had. In that case, it's really about unsupervised learning, detecting structures and clustering things, etc. So it's about self-supervised learning as well, and where it can be useful again to exploit synergies between synchronized sensors. So I'll just go through examples of that. So in terms of pure work of annotation, when people, I showed before an example of a tool to annotate point clouds, where the annotator is just looking at the point cloud. But for some of the things that you want to annotate, it's just not possible if you don't have the video at the same time. So this is an example from Scale AI, which is one of the biggest player in the field of annotation, in particular for automotive, but not only. So they have tools. This is just a snapshot from their tools, where in order to annotate the point cloud here for the 3D boxes, the cuboids, you do that at the same time with you see the picture-in-picture with the images of the same scene, and of course it's really a big help for the annotator. And likewise for semantic segmentation. So imagine the task of semantic segmentation of the point cloud, meaning that each point in the cloud has to be semantically labeled, so it's quite difficult. So this is here sort of in the user interface almost, where you leverage the multimodality. So another example of this cross-modality, cross-modal annotation transfer is the one. So I already showed this example earlier of this Valeo Radar dataset, and you see the three views of the classic three views of the radar data with range, angle, and Doppler. And if you want to annotate that in the raw data, not very easy. So essentially, what we did in this work, which is mostly about the dataset that we published and released. So we wanted to annotate the objects, in this case, three types of objects: cars, pedestrians, and cyclists, both in the radar signal with points, boxes, and segments. This you can see on the right. And to do that, we actually annotated the video automatically. So just object detector, bounding box object detectors. And because well, it's not so simple. It's not like with point clouds. It's not so trivial to sort of align that with the radar data. But we had an automatic pipeline to do that, and this is how we got the annotation of the radar data. Then we had to clean a bit, but mostly the pipeline was fully automatic. Was almost fully automatic. And using just to say how we use this data set, we then using the data set, so this is what is called the radar tensor. At a certain time, we just learned out of this the tensor you can build three different views, 2D views, in sequence through time, and then we just we had different attempts with different architectures, but we had this convolutional neural network with different input streams, 3 of them, and then we set the task of segmentation of 2 of the views using our annotation and this is how we train the model. And then you can relate what you have detected or segmented in this case in the two views of the radar cube, and it's related to actual objects in the visual scene. But this is just an illustration. Just to show that we were in this case it was successful. So it was just to illustrate the use of this type of fully automatic annotation of quite not so easy to annotate data. Another example, still a recent one from our work, is still about radar in this case, but it's HD radar, so way more complex and way bigger type of data. And in this work, we had, so in the data set, we had a front camera, a lidar, and this HD radar. And we wanted to address two tasks. One is car detection, essentially, and what is called free space segmentation that you see in green on the left image, which is essentially where the car can drive, at least safely enough. And you see then the annotation, again, same story. Annotations then are boxes for the vehicles and the segmentation of the free space, and you see it in the different views, either of the radar data or just in the bird eye view in the third column. And similarly, to do this annotation, what we did is first automatic annotation of the images, and then it was automatically transferred to the radar. And last example, which is ongoing work with in collaboration with CTU in Prague. In this case, it's for exactly the task I showed done manually earlier. Is the annotation of the bounding boxes for vehicles and for road users in lidar point clouds. So what you see on the screen is an accumulation of different scans of the scene, and so what we did is in order to annotate, so we have already manual annotation of key frames, so one scan every don't remember exactly, but we don't have the annotation of the free sequences. And what we want is to train the best possible 3D object detector from the point clouds. And so what we do is to train first sort of a super model which can use the future, something that of course, you don't have access to at runtime. So you have using the supervision of a scan and using the past and future scans for which you don't have the actual annotation. We train the first model using all this information, and this model then becomes the teacher. So it's about distillation. Will become the teacher for the actual model that you train, which is then a sequential model, not an offline model, and which is the one that you will use effectively at runtime. So it's one example where you train first sort of a luxury model for which you have less constraints, either it's a bigger capacity or it can use, in this case, future information that is not available at runtime, etc. And you use this new model in order to annotate or which is one way to distill information, or at least to drive the learning of the student model. And what you see, I forgot to say here, the boxes that you see in red are the boxes that have been recovered thanks to the result of the detector without access to this information is in blue. Green are the ground truth points. In blue, these are the detected objects without access to this privileged information. And red is the one you obtain with a sequential model, but which has benefited from the knowledge of the teacher, which was trained with the future information. So it's quite effective. Yeah, good time with it. I think I'm going to skip that. But this is the thing it's an ongoing work that I referred about fully unsupervised semantic segmentation, which is using self-supervised learning. I just want to briefly mention a last thing, which is creating or controlling new scenes, where you can then have sort of automatic annotation again. In particular, using the progresses of generative adversarial networks, which are getting every year more and more impressive. So these are examples from the third version of StyleGAN from NVIDIA. So these high-res, super photorealistic images of people or portraits are completely fake, and they're just generated at random using random input. And now on top of that, there are more and more ways to control the actual. It's not only random input, but you can control to some extent the pose, the lighting, the expression, either because you train your GAN this way, or because after the fact you can sort of control in a post hoc fashion an existing GAN. Or one way also to control that is to have to learn a conditional GAN, where part of the conditioning comes from your what you want in the scene. And I have an example of that, which is Oasis, for instance, where you can see it's one example where you can have as an additional input a semantic map, saying for each pixel what is the semantic class, and you can generate a diversity of scenes which all respect this semantic map. And so this is very useful if you want to produce new scenes with some control, and these scenes being used for training in particular. So this is exactly the point here. So you can try at least to use these generative mechanisms to create training data, either fully generative training data, or in combination with real data, or by changing something in a real scene using a GAN. I'm going to show one example of that. And by this you can access new type of scenes or new conditions while controlling the annotation. But of course, it's not so obvious. First of all, in particular, if you want to train from scratch your own GAN for that, it's notoriously difficult. So the alternative is just to exploit existing off-the-shelf pre-trained GAN, but then there is the question of how to control the output. If you want to use that in order not to generate ex nihilo the scenes, but modifying existing scenes, in that case, you have an additional problem, which is you first need to embed your original real scene into the semantic space, the latent space of your GAN in order to do the modification. And there are different ways to do that, which are more or less effective or more or less complex or expensive. And the last thing is really how to assess the quality of this training data. Of course, one way is to use it for downstream tasks, but then there are different regimes with. So it's not completely trivial to assess in a very meaningful way the quality of your generative data, depending on how you want to use it. And it's one of the challenges in the GAN paper, I feel. Anyway, let me show you for the remaining minutes some examples. We have two examples actually. One, which was again in collaboration with the Czech Technology University in Prague, where the idea we had is you see on the right what is usually done when testing with dummies, like there are puppets on the test track to try to test, in this case, emergency braking. It didn't work very well in this case. The idea is to have synthetic pedestrians in real scenes in order to train, or actually to test, although we use that mostly for training, actual models. So in a nutshell, maybe I'm going to skip the synopsis. What we did is that we train a GAN which, given a given pose of a human, a given scene, and a given location in the scene, is able to create a fake human in the scene. So you see here examples. In each of these scenes, there is at least one artificial dummy. Of course, it's easier to spot in the scenes where there is a single person. But you see here, it's what we did that either in crowded scenes or in nighttime or wintertime scenes, etc. And we use that in different protocols to test the usefulness of this. Oh, by the way, just two examples here where I show explicitly who are the fake pedestrians. On the left is fairly good. On the right is not so good. Actually, is naked foot, I think. But it has the right sort of texture, and it blends in. I mean, if you don't look at the blow up version, it blends in fairly well in the scene, and it turns out to be good enough to be useful for training, even if for the human eye there is something a bit weird. And just to prove the point, I'm not going to explain the numbers on the right, but if you look at the image on the left, what you see is that it's a low data regime where we train a fairly simple object detector on limited annotated data first, and on the test image you have the blue detection. Actually, there is a true positive and I think a true negative, and then we augmented the data set with all these synthetic humans, and we retrain the model, and then we have the new performance with, in addition to the blue boxes, we detect the green one, and so we recover a lot of the misdetections that the first model produced. So it proved effective. What is still at this stage a bit disappointing or preliminary is that it has proved useful in extreme regimes where you have low capacity model or little annotated data. But there is a good signal here that this generatively augmented data can be useful for some cases. And actually, we had some conclusions for nighttime, which is a real use case, in order to get better nighttime detection using images, nighttime scenes in which we have very few, if any, pedestrians originally in the scene, and then we augment that. And the last examples I wanted to show, and I will finish with that, is this work we had at CPR, which we call Semantic Palette, and the idea was to control the generation of driving scenes by the proportion of classes. So essentially, it's a two-step pipeline where you have a first GAN to produce the semantic layout, and the second GAN, which is off the shelf, which is actually the one I showed before, where you can produce a scene given a semantic layout. So our work here was just in the first step how to control the generation of the semantic layout if you fix or you have a target class distribution. So we found mechanisms to enforce that through normalization and some layers in the GAN. You can see that as a form of modulation as well. And I'm just showing results here. So what you see on the top part is a first target class, target histogram of classes, and you see three scenes which have been generated, and they respect very closely what were the target proportions, and the same on the bottom. And actually, if you look at the yellow bar in histogram corresponds to the tuk-tuk, and you see so the color codes matches with the classes in the images, and you see that indeed in the three examples you have the right proportion of tuk-tuk labels, and they translate into in the scene with the appearing of these vehicles. And the other thing we had is that in order to use that as a mechanism to produce training data, the histograms themselves, the class proportions, in this case, either you fix them by hand, and actually it can be useful for image editing. This is another story. But for producing training data, what we can do is that we just learn the distribution over the class histograms for from an actually annotated data set. So then we can sample the class histograms, and then for each sample, then we can generate one or several scenes. And this is how we used it, and it was we had interesting results as in terms of when training a segmenter on this generated data. So let me finish with just a few points. So really the goal here is the message is that it's very important. I mean, better models, new architectures, obviously, including with transformers, they are key. The data is key as well. And in order to get the best data possible for the challenging things we have in particular for autonomous driving or assisted driving, we have to make use of all the resources we can put our hands on: real data, synthetic data, annotated, not annotated, etc. And then we have all these mechanisms to transfer or factorize out the information across the data sets, all the way to self-supervised learning, which is becoming more and more powerful. One thing that I don't really mention, I was really focusing on training data, so the data which is used to train machine learning models. But there is another part of the story which is very important for these driving systems, which is the actual testing. So it's validation testing and all the way to certification to be allowed to have them on the roads. And there you need as well new data, which is annotated, and the metrics are not necessarily the same. And it's in particular you need to assess the worst case performance. You need to discover corner cases, like the very rare situations which might be very annoying, and you have to discover them in large amount of data which is not annotated. So it's a problem on its own. So I'm just mentioning it. And last thing I want to say is that I mentioned that at the very beginning. So of course, the performance of the machine learning models is increasing fast, but it's not always about, in our cases, it's not at all only about this accuracy, pure metrics that we have in classic academic benchmarks. It's also about the robustness of the models, or the ability to work good enough in completely new situations, out of distribution input, etc. So we need to be able to detect that it's an out of distribution input. We need to be able to predict that there is a good chance of a failure, and we need to have a good enough understanding of the world, which also leverages physics and knowledge of the world. And this is clearly a very important route towards safer systems. And with that, I'm going to stop, and I'm already a bit late. Thank you for your attention.
Thanks, Patrick. It was a great presentation. I enjoyed the last part. It's kind of image composition with using GAN. I think that's the way to handle the imbalanced data and handling long tail label distributions. I think that's the way you can generate a lot of fake examples with different combinations of the scene and objects, and then create or kind of balance your data, I would say.
Yeah, I think it's promising. Not very easy to, as I said, not completely easy to demonstrate the full power of this as per now. And for this reason, not so easy to publish, by the way, because I mean, reviewers quite rightly are really challenging on the performance, and that really the reward of all the merit of this new data. But yeah, I think it's a venue which is quite interesting. And here we are just talking about sort of instantaneous perception tasks. So if you imagine now having augmenting dynamic data, it's sort of the next level in terms of challenge. If you want to include an actually walking person in a sequence of images or point clouds, etc. Yeah, but it's also related to data augmentation at large.
So Alex has a question, please.
I have two. Maybe I wanted to follow up on this discussion on, so you are artificially putting pedestrian in real world scenes, right? And so I like it a lot also. But do you, I'm sorry, I did not read the paper, but is there any special reasoning on where you take this pedestrian from? And what kind of diversity, or do you have any study on, like in this data set, here is the distribution of my pedestrian from viewpoint, appearance. This is maybe missing, and I'm gonna generate.
It was not a systematic or formal study of what is missing and that we wish to cover with the generated pedestrians. It was more like the motivation was there, and to be very precise, for instance, we know for sure when the car makers test some of the, say, emergency braking system, etc., they have a long list of things which should be tested. Typically, what about if you have a crouching kid
Exactly.
around the car? So this is the type of things for which you cannot have data.
Absolutely.
For obvious reasons. And so this was the sort of motivational examples we have in mind, but we didn't cover that systematically. The only thing we did is that we had a way to generate the pose, which was more like based on the distribution of human poses in annotated data set with the limbs. So in a sense, we were still generating classic poses. But we had examples which were more like a bit cherry picked, or where are we using skaters, or I mean, we were also using a bit extreme poses in the work, but we didn't explore systematically this aspect. The idea was really to have the tools for that effectively, but it's still missing.
But the generator of pedestrian is learned from a different data set.
There are three inputs to the system. You need the scene, the place in the scene, and the 2D pose. So the 2D pose is generated from a distribution of poses, which was from not remember now. I guess maybe it was Coco. So not even road scenes.
Thanks. And my last question is, which is a question I get a lot also, I want to hear your answer, is when we, how can you ensure that deep learning based detector will always detect what you need?
I guess it's not only for detectors, by the way, but it is the sort of super challenging question of verification of a system.
Exactly. Yeah.
Which is absolutely crucial for driving, but also for flying things. And you have regulations. You have and I think as far as I understand, as far as I know, after now a few years in this field, nobody has the answer. So there is you have the tools from the sort of software tradition, which is software verification, etc. Even how to prove things, how to prove the performance of a neural network for this task. I don't know. Apart from having, I mean, you can guarantee that for some inputs, if you perturb it in some way, even guaranteeing the robustness to adversarial modification, we don't know how to do. And to make things worse, and I'm afraid my answer is not an answer, but more questions. So your detector is just one brick, is just one task.
Then you have many more.
So at the end, you have functions.
Yeah.
So a function can be level 3 driving, can be parking, can be emergency braking, can be adaptive cruise control, and you need actually to of course, validate the full function, and the function is composed of so many modules. So we have also to test the full system, and it's yet another issue. But I think at large, the community of machine learning working, at least for the people working on safety critical systems, they really need to seriously look at this question. And one related question is, at the way we test in sort of the academic benchmarks, the way we test our systems doesn't tell you, well, it tells you a bit about the runtime performance, but the real world performance of your systems, sometimes you have no real idea what's going to happen in terms of catastrophic failures, etc. So out of distribution, for instance, performance is really important to assess. And I don't know how to do that. I mean, I have some leads, and we work on different things, like many people in the community, but that's very challenging. So I guess we will continue the discussion.
Yeah, we have to discuss it around the coffee. Thanks.
So we have more questions, Jean-Marc and then Said.
Yeah, hi, Patrick. Nice to see you. Unfortunately, you are not physically here, but yeah, so thanks for the great talk. I had maybe two questions. So you presented lots of transfer learning with different methods and so on, but it's always the point of view of the car. I was wondering if you would have a system which is like seen from a pedestrians, a pedestrians looking at the scenes. I mean, do you think that would create some challenge, or the data from cars could be transferred to pedestrians? Because to some extent, it's quite a different view, especially for pedestrians which are trying to cross streets, right? Or do you think that no, the data will be large and so diverse enough to cover this kind of scenes?
Okay, so to which extent things can be transferred to
pedestrian, to pedestrians view.
Pedestrians, but even from one car setup to another, it's already to some extent a challenge if you don't have the same setup for the sensors, which is already the case across the publicly available datasets, but which is also on our projects, like with customers, different from one project to another. So transferring from one setup to another, sometimes, I'm afraid I'm going to make a sort of ambivalent answer. Sometimes it's surprisingly difficult, and some of the times it works surprisingly well. I'm taking one example. So we work a lot with fisheye cameras, which are wide angle, low mounted cameras compared to a pinhole front cam, and things that we train on public datasets, which are pinhole front cam usually. Well, not always, but okay, highly mounted. They transfer pretty well to low mounted fisheye. So which means that it might be the case that if you have now an ego person as opposed to ego vehicle viewpoint, like a pedestrian with some device, some of the things might transfer a lot quite well, which is also even opening a bit more, given the progress that we see, and also even now in our works on the self-supervised learning of representations. The hope is that it does capture something which is intrinsic to the road or the street scene, irrespective of the viewpoint. Then it also depends on which sensory modality. So camera and point cloud are fairly different, and things, I mean, the things which transfer well or not so well is not necessarily the same between whether you consider cameras or you consider point clouds. But it's an interesting. Last thing I want to mention on this front is that the question also applies to the sensors which are on the infrastructure, and we actually do work on lidar to be used on poles over pedestrian crossings, for instance. So there are other ways also to change the viewpoint, but in that case, it's a fixed viewpoint where you have the sensor which is part of the infrastructure. And I think it's very interesting as well, and very promising as a way to have, again, safer infrastructures. And So I guess what would be good at the end of the day is to have data from all these viewpoints and to use them in a very very ambitious self-supervised learning approach for this leveraging all this data, which we don't have yet. We don't equip pedestrians.
Yeah, thanks. So maybe just a quick question because time is running. Yeah, also you presented a lot of static things. You mentioned a bit about dynamics, right? And you mentioned some of these cases. So how difficult is it to move towards dynamics and beyond maybe trajectory, right? I mean, it is.
So obviously there is one aspect to stay in the theme of the presentation, which is annotation. Very difficult to annotate, but of course, as we know also from the good old days of visual tracking or tracking at large, I mean, you can to a large extent automatize the annotation. So you select one object and then you track automatically, etc. So let's assume that we can have a good annotated training data. So when it comes to dynamics, we are facing very specific challenges for driving. So scenes can be extremely cluttered, so a lot of occlusions. And one thing that we need for in the full stack of the driving system is not so much tracking, but it's forecast. And forecast, and I know that Alex is doing a lot of things on that front. So forecasting the trajectory of the road users, whether they are vehicles or pedestrians or cyclists or whatever, all the road users, it's something very difficult. So typically we want to predict a few from 1 to 5 seconds ahead. 5 seconds is quite a lot, depending on the speed. And what is very difficult is not only want to forecast a few seconds ahead, but these are multiple interacting agents. And on top of that, ideally you want not to forecast one, but several possible futures. And that's coming back to the training data. You don't have in your training data, if it's real data, you don't have multiple futures by definition. So it's a very challenging thing.
Yeah, including evaluation, but yeah.
For the same reasons.
Yeah, exactly. Yeah.
And this is where synthetic environments like engines, simulation engines can be useful to some extent, at least to play with this idea of multiple futures.
Okay. Thank you, Patrick. Thank you.
So, Said, you can ask a question.
Thanks. Thank you for the presentation. It was very interesting. So yeah, just very short question. Following up the first question of Alex, the work that you put pedestrians on the road. Like I was wondering if there was any drawback or some kind of trade-off when you use these kinds of generated pedestrians on those. Like, was there any false positive, for example, or I don't know, like it was only better in nights, or for example, do you lose some performance for detecting pedestrians during the day, or I don't know, anything?
It's not something that we noticed. The risk is that if you rely only on the fake pedestrians, is that some of the artifacts might be picked up as a spurious correlation by the detector, and then it won't find this at runtime, so it will probably perform less well. But it's not something we noticed. What you asked. At the same time, as I was saying, we struggled so much just to demonstrate, and to be completely honest, at this stage at least of things, it was so difficult to really find the good setups where it was beneficial. I mean, it was never detrimental, but demonstrating how much and to which extent it's beneficial was quite difficult, because it's beneficial in certain conditions, and in particular the one I mentioned, which is low data regime. And in the experiments we have always, except for nighttime, indeed, where we had this extreme experiment where in the night scenes all the pedestrians were at training time were fake, and we didn't notice the downside that you mentioned. But most of the time we had a mix of real and fake, right? So
yeah, so if you have a lot of real data, like, then probably this is less effective, or is it harmful? I mean, this is my question.
At this stage, this is less effective, except, and it ties back to the discussion with Alex. Because we don't have yet this type of protocol where we can really sort of assess on very specific type of situations which are key for security. So we don't have that necessarily, at least in the public data sets, etc. But I think what would be important in the future for future work is to make sure that for certain scenarios, like I was mentioning, the little kid playing or running behind his toy near the car, and this, so that we have a list of very specific scenario for which we really demonstrate that by using synthetic augmentation, we have way better, in particular, true positives, without degrading the overall performance on the sort of situations, and this requires quite a very careful work on the testing. We haven't done that.
Thanks.
We can take one more question before finishing, if there's any. No? Perfect. Okay, perfect. Thanks again, Patrick. It was great presentation. So guys, thanks.
Thank you, everyone. Merci, Patrick.
Have a nice day. Bye-bye.
Bye.
Right, yeah. Have a nice day. Bye.
Bye.